Hello, today we discuss even and odd permutations. Using the properties of this permutation, we classify those into two categories: even permutations and odd permutations. Okay, using this definition, we can see some interesting example of subgroups of this permutation group Sn. So we start with the definition of transposition. Transposition is a cycle with a length 2. So we start with the definition. This is a definition 9.11. A cycle of length 2 is called a transposition. Now we have seen what is a cycle. A permutation can be written as a product of cycles, and in the last class we have seen the disjoint cycles commute. Okay, so using the definition of cycle, you can easily define length of a cycle of length 2. Okay, if a cycle contains two elements, two symbols, then that cycle is called cycle of length 2. Those cycles are also called transposition. Okay, so using this transposition, we can easily define even permutation. So first of all, we identify some properties of a arbitrary permutation. Say sigma. Say we write the sigma as an element of S6, 1, 2, 3, 4, 5, 6, and I write this is the I define the sigma as a cycle. First of all, we write this is 5 goes to 4, 4 goes to 6, 6 goes to this 2, and 2 goes to 3, and 3 goes to 1. Okay, so this defines a cycle, because we can write this as a cycle. 1 goes to 5, 5 goes to 4, 4 goes to 6, 6 goes to 2, and 2 goes to 3. So this defines a cycle in S6. Okay, but the cycle has 6 symbols, so this is called a 6 cycle. Okay, or cycle of length 6. Okay, similarly, we can write the another permutation gamma as a permutation 1, 2, 3, 4, 5, 6. So if we take this as this one goes to 1, 2 goes to 4, 4 goes to 5, and 5 goes to 6, or 5 goes to some 2 itself, then this is 3. This 3 and 6 are fixed. Then you write this as a cycle of since this one is fixed, we start with 2. 2 goes to 4, and 4 goes to 5. 5 goes to 2. So this completes one cycle, and all other symbols are fixed. 1 goes to 1, 3 goes to 3, 6 goes to 6. So this gamma is an element of this S6 called cycle of length 3. Okay, so in the similar fashion you write cycle of length 2. So for example, some alpha that is equal to 1, 2, 3, 4, 5, 6, and we write this is 1, 2, 5, 4, 3, 6. So this is a cycle. 3 goes to 5 and 5 goes to 3. So this permutation can be written as a cycle 3 goes to 5. Okay, so this is what we called a transposition. Okay, since this is a cycle of length 2, so these types of permutations are called cycle of length 2. Okay, that is nothing but transpositions. Okay, now onwards for the time being, we are discussing with the 2 cycles. Okay, so we know that there are other permutations which are not cycles in Sn. Okay, so if we write another permutation, say beta is 1, 2, 3, 4, 5, 6, and I'll write this is 3, 2, 1, 4, 6, 5, then this can be written as a product of cycles. Okay, product of disjoint cycles. So once you got beta, then you can start with a symbol which undergo the changes. So 1 goes to 3, 1 is changed to 3 first, then 3 goes to 1, so this cycle is completed. Then 2 goes to 2, so 2 is fixed. 2 is a single cycle of length 1, so that can be identified as identity, so we can skip that one. And 4 is also fixed. Then 5 goes to 6 and 6 goes to 5. So this completes another cycle. So this beta is nothing but a product of two transpositions or two disjoint cycles. Okay, so if you have any arbitrary permutation in Sn, that can be expressed as a product of disjoint cycles. Okay, so this is a product of two disjoint transpositions or cycles, a cycle of length 2. Okay, similarly, another permutation you can write is 1, 2, 3, 4, 5, 6. I'll write this as 3, 1, 2, 4, 6, 5. So this is another permutation in S6, and it can be written as a product of two cycles. One is of length 3, that is 1 goes to 3, 3 goes to 2, and 2 goes to 1. So this completes one cycles, and we have other symbols which undergoes the changes. So 5 goes to 6 and 6 goes to 5. Since this was fixed, then we skip that 4 and we write this as 5 goes to 6 and 6 goes to 5. So this gives the disjoint, this gives the expression for delta as a product of disjoint cycles. So this is 3 cycles in times 2 cycles. Disjoint cycles 3, 1, 3, 2 into 5, 6. Okay, so any permutation can be written in this manner in Sn. So once you got a cycle, if suppose we have a cycle, I'll write the symbol for cycle. First of all, we can take this the first example, 1, 5, 4, 6, 2, 3, 1, 5, 4, 6, 2, 3. So this is a cycle in S6. Okay, so once you got this cycle, then this cycle can be, any cycle can be written as a product of transpositions. So those transpositions need not be disjoint. If we write the permutation as a product of disjoint cycles, then these expressions are called cycle structure of this permutation. The cycle structure of delta is this one. Cycle structure of this beta is this one. Okay, so this defines the cycle structures. Cycle structure of a permutation, an arbitrary permutation. So this gives the cycle structure. So if you are given a cycle structure, then you can see disjoint cycles in that expressions. Okay, if you pick one such cycle in that expression, then that cycle can be expressed as a product of transposition. Okay. That means if you are given this one such cycle, then this 1, 5, 4, 6, 2, 3 can be expressed as 1, 3, a transposition 1, 3 times 1, 2 times 1, 6 times 1, 4 times 1, 5. Okay, that means we constructed these transpositions using 1, 3 first. First you take 1 and this 3, then you take 5, then you take 1 and 2, then you take 1 and 6, then using 1 and 4, then using 1 and 5. So this is the way we constructed these transpositions. So once you take these transpositions, then you can write this 1, 5, 4, 6, 2, 3 as a product of these transpositions. Okay, so how will you verify that? In order to first of all, these LHS and RHS are all permutations. The right side is a product of permutation, so this is again a permutation. So left side and right side are permutations. Permutation means functions. Okay, so how will you verify the equality of two functions? By looking into the images of elements in the domain. Okay, so these are the 1, 2, 3, 4, 5, 6 are the symbols in the domain. So we have to verify the images of each symbols in both sides. Okay, so first of all we take what is the image of one in right side. So what is the image of 1? So in order to get the image of 1, you need to multiply this from the right hand side. Okay, first of all, 1 goes to 5 here. Okay, this is the way we multiply this permutation. So 1 goes to 5, this is the easiest way. And that 5 is here, we have 1 goes to 5, and that 5 is fixed here. There is no symbol 5 in this expression, and in the rest of the expressions there is no 5. Okay, so we can say that ultimately 1 is mapped to 5. Now we will have to evaluate image of 2. Okay, so first of all you look into this one. 1 goes to this is the first transposition. So in this 2 is fixed, since this does not contain 2. So 2 is fixed here. So 2 goes to 2 here. Then you look into this one. Okay, here we have 2 is fixed, and here we have 2 is fixed, and here we have 2 is mapped to 1. Okay, so here we have 2 is mapped to 1. Then in this again, that 1 is mapped to 3. So that 1 is mapped to 3. So ultimately 2 is mapped to this 3. So we can say that image of 2 is 3. Okay. Similarly, you can find out the image of 3. Okay, how will you get the image of 3? So first of all, you observe this one. Again, 3 is fixed here, 3 is fixed in the next one, 3 is fixed in this one, 3 is fixed in this one. Only this only in this transposition 3 undergoes the changes. So 3 goes to 1, 3 goes to 1 here. So 3 is ultimately mapped to 1. Okay. Similarly, you can write the image of 4 by looking into the product. 4 is fixed here, and this 4 is mapped to 1 here, and that 1 is mapped to 6, and 6 is fixed here and here. So we have 4 is ultimately mapped to 6. Similarly, 5 is mapped to it. How will you get the image of 5? First of all, look into this one. 5 is mapped to 1. That 1 is, so 5 is mapped to 1 in the first one, and that 1 is mapped to 4 in the second one, and that 4 is fixed here, 4 is fixed here, 4 is fixed in the other transposition. So ultimately, image of 4 is image of 5 is 4. Now we have image of 6. So first of all, observe this one again. Image of 6 is 6 because this fixes the 6, and here also 6 is fixed, and here 6 is moved to 1, and we can say that image of 6 is 1 in this permutation, and that 1 is mapped to 2. So this is 1, this is mapped to 2, and 2 is fixed in this one. Okay, so ultimately 6 is mapped to 2. Now you observe the images of the same symbols in this expression. Okay, so what is image of 5 or image of 1 in this one? Image of 1 is 5. Okay, then image of 2. How will you get image of 2 here? Image of 2 is 3. Okay, so what is image of 3? In order to get image of 3, you write this 3 is mapped to 1. So 3 is mapped to 1, and image of 4. Where the image of 4 is 6. Image of 5. Image of 5 is 4. Image of 6 is 2. So when you observe these two images of symbols, then we can say that these two permutations are same. Okay. Now this proves the general case. In the next, in general, we can say that if you have a permutation in Sn, arbitrary permutation in Sn, say A1, A2, etc., A, some R, then this can be written as A1 AR, A1 AR minus 1, etc., etc., A1 A2. Okay, so any cycle can be written as a product of transpositions. So these transpositions need not be disjoint, because A1 contained in every transposition. So you cannot expect this as a disjoint expression. But if you are writing cycle structure, then that is a product of disjoint cycles. Okay, so if we move on to transpositions or product of transposition, that need not be disjoint. Okay, so once you write this expression, you can say that this is 1 3 1 2 1 6 1 4 1 5. So this we can write this this permutation or this cycle can be written as product of transposition as 1 3 1 2 1 6 1 4 1 5. Okay, so this is the expression of sigma as a product of transposition. Similarly, you can write this. This is a product of two transposition 2 5 and 2 4. So this gamma is also written as a product of transposition. So this is itself a transposition. You need not worry about that. And this is again a product of transposition. So this is not a product of transposition. So it can be written as, first of all, you write the first 3 cycle can be written as 1 2 into 1 3, and you adjoin this 5 6. So every permutation, so the inference is nothing but any permutation sigma belongs to Sn can be expressed as a product of transpositions. A product of transposition. Deliberately I'll skip the word disjoint, because this sigma need not be a product of disjoint transpositions. Okay, so there are permutations which can be expressed as a product of transpositions, but in general the sigma need not be a product of disjoint transposition. So I write this as a product of transposition only, not the word. I am not using the word disjoint. Okay. In the next class, we will discuss some interesting results as a consequence of this definition and this idea A1, A2, A can be expressed as a product of transposition. Okay, thank you.